This is stochastic processes, module 8, renewal processes. In the first 3 lectures, we have discussed the renewal process and its properties. Then later we have discussed the important limiting theorems on renewal processes. Then we have discussed the Markov renewal process and Markov regenerative process. In between, we have discussed the reward renewal processes also. In this lecture, we are going to cover the non-Markovian queues with respect to the service time distribution. In particular, we are going to discuss the MG1 queue and the MGCC system. What is MG1 queue? In this queuing model, the inter-arrival times are exponential, but the service times are non-exponential, nothing but general distribution. Assume that the CDF of the service time is f of t with the mean 1 by mu. So suppose you assume that service time is exponential distribution with the mean 1 by mu, then it is a MM1 queuing model. Let Nt be the number of customers in the system at time t. In this model, the evaluation of the system after the arrival of a customer depends not only on the number of customers n of t, but also the remaining service time of the customers receiving service. The remaining service is nothing but, since the service times are random variable, the remaining service time is the elapsed service time or remaining or residual service time. Whenever the service times are exponential distribution, the remaining time or elapsed service time or residual service time all are exponential distribution. Whenever the service times are not exponential distribution, then the remaining service time will be a some other distribution. The evaluation of the system after the service completion depends only on the system of the state. In this queuing model, the system changes the state based on 2 types of transition epochs. One is the arrival epochs and the other one is the service epochs. First, we are discussing the arrival scenario. The evaluation of the system after the arrival of a customer depends not only the number of customers n of t, but also the remaining service time. Whereas the evaluation of the system after service completion depends only on the state of the system. Therefore, n of t is not a semi-Markov process because it depends on the remaining service time. Since after the arrival of a customer, the remaining service time also play a role, whereas after the service completion, it depends only on the state. If you recall the definition of semi-Markov process, the memoryless property will be satisfied at all time transition instants. The memoryless property will be satisfied at all time transition instance, then only the stochastic process is called a semi-Markov process. Therefore, here the n of t is not a semi-Markov process. Suppose the time origin is taken to be an instant of a departure which left behind exactly j customers, then every time the departure occurs leaving behind j customers, the future of n of t after such time has exactly the same probability law as the process had starting at time 0. So this is so called the probabilistic replica with the Markov property as well as the time homogeneity. If you recall the definition of a Markov regenerative process, A stochastic process has the property of a probabilistic replica with the few time instants. It has the Markov property with the time homogeneity with the few states, at few states. Therefore, N of t is a Markov regenerative process. Please refer the previous lecture for understanding the definition of a Markov regenerative process. So, by using the definition of Markov regenerative process, the N of t will be the Markov regenerative process if you consider the time epochs or departure time epochs. Let nth customer departure at the time instant Tn. Let Xn be the number of customers in the system just after the departure instant of nth customer. That means Xn is nothing but the n of Tn plus 0 just after the departure instant of nth customer. That will be treated as the random variable Xn. Then Xn comma Tn will form a Markov renewal process. The Tn are the time instant at the departure epochs, not the arrival epochs. Only the departure epochs, that collection of time points along with Xn form a Markov renewal process, where Xn is n of Tn plus 0. That in words, it is the number of customers in the system just after the departure instant of nth customer leaves. We can create a semi-Markov process by y of t is equal to xn if that value will be between Tn to Tn plus 1. If it is the same, then it will form a semi-Markov process. That means the system is not moving any other states in between the time duration. Then the y of t will be a semi-Markov process. As such, n of t is not a semi-Markov process, whereas xn comma Tn will form a Markov renewal process, and the n of t will be a Markov regenerative process. With the embedded, the y of t will be a semi-Markov process if I make y of t is equal to xn, where t lies between Tn to Tn plus 1, and having the embedded DTMC xn. Our interest is to find out the steady state measures. To obtain the steady state probabilities of yt, we need the one-step transition probabilities of embedded DTMC. Suppose these time points Tn are the regeneration points, then the Tn's will form a renewal process. Let An be the random variable denoting the number of customers that arrive during the service time of nth customer. That means xn plus 1 will be an plus 1 if xn was 0. If xn was greater than or equal to 1, then xn plus 1 will be xn minus 1 plus an plus 1. That is nothing but how many customers in the system when the n plus 1th customer leaves. That is same as when the nth person leaves, how many customers in the system. Minus 1 is for the n plus 1th customer himself. And how many customers enter into the system during his service, that is an plus 1, whenever the xn was greater than or equal to 1. If xn was 0, then the number of customers will be in the system when n plus 1th customers leaves will be same as number of customers who enter into the system during his service time. Since the service times of all the customers have the same distribution, the distribution of an is same for all n. Therefore, you can go for For all n, we can go for AR is the R customers enter into the system during the any customer. So that is the probability mass function of a AN. Now we can find out the transition probability of a system moving from the state I to J with respect to the stochastic process Xn. Xn is a embedded Markov chain in the n of t. So that will be Aj if j is greater than or equal to 0 and I equal to 0. Similarly, Aj minus I plus 1 or 0 according to the values of I and j. Now we can make a one-step transition probability matrix that is nothing but the P. The row sums are going to be 1. Note that Xn is a irreducible Markov chain because each state is reachable by every other states. If you make a row that is nothing but lambda by mu is less than 1, lambda is the parameter for the inter-arrival time, which is exponential distribution. So whenever rho is less than 1, the chain is a positive recurrent. Rho is less than 1 is required because only then the mean recurrence time will be finite. Hence, the Markov chain will be a positive recurrent. Therefore, it is a ergodic. Irreducible positive recurrent gives the Markov chain is ergodic. Therefore, the Markov chain is the embedded Markov chain is ergodic. So we can find out the limiting probabilities that will exist as well as it is independent of initial state I. You can find out the limiting probabilities by solving V is equal to Vp and summation of Vj is equal to 1. The solution can be obtained by using the probability generating function of V's and A's. V's are probability vector, steady state probability vector, and A's are the number of customers arrived during the service of any customer. So Az is nothing but the probability generating function for Aj's, and V of z is nothing but probability generating function for the random variable for the probabilities Vj's. Now you can find out A of z in terms of the Laplace transform of the function f of t, because A of z is nothing but the summation of Aj into z power j, and you can replace Aj by the integration. Now integration and the summation can be interchanged, and f of t is nothing but the distribution of service time. F of t is nothing but the distribution of service time. Therefore, the small f of t is the probability density function of the service time. So the f star is nothing but the Laplace transform of f of t. So the probability generating function of A of j's is nothing but the Laplace transform of the probability density function of service time distribution. Now we can find the expected number of arrivals during the service time. That is nothing but, since we got the probability generating function, differentiate with respect to z and substitute z is equal to 1 will be the average number of arrivals during the any customer's service time. So you can simplify that by using the chain rule. So that will be nothing but lambda by mu, where lambda by mu is nothing but the rho. So the expected number of arrivals is rho. Rho is nothing but lambda by mu. our interest is to find out the steady state probability is Vj's. So the Vj's you can relate in terms of by expanding V is equal to Vp, you will get Vj is equal to V naught Aj's plus summation form. So multiply z power j in both sides and taking the summation, you will get after simplification you will get Vz in terms of Az with the V naught. V naught is V naught is the steady state probability of Vz in terms of Az and V naught. You know that since V of z and A of z are probability generating functions, so V of 1, A of 1 are equal to V1. So using that relation, you can find out what is the value of V naught. So V naught is nothing but 1 minus A dash of 1, and A dash of 1 is nothing but the expected arrivals. Just now we got expected arrival is equal to rho, therefore V naught is equal to 1 minus rho. So earlier we got Vz in terms of A of z with the V naught, and already we have the relation A of z is a Laplace transform of a probability density function of service time distribution, and just now we got V naught in terms of V naught is equal to 1 minus rho. Therefore, the probability generating function of the steady state probabilities will be in terms of Laplace transform of a probability density function of a service time distribution with rho, and this equation is known as a Poloczyk's-Kenshin or PK formula. So this is the formula used to find out the steady state probabilities, because if you get the coefficient of z, that is the steady state probabilities. Note that the quantities of interest are the steady state probabilities at a different set of points, namely the arrival epochs. From the point of view of arriving customer, the number of customers that he finds in the system, not the number he leaves behind, is the quantity of interest. Since the arrival follows Poisson process, the equilibrium distribution of the number of customers found by the arrival and the equilibrium distribution of the number of customers left behind by a departure in this queuing model are the same. Note that the Mg1q, the limiting distribution of the number of customers in the system at the arrival epochs, at the departure epochs, and at the arbitrary time points are the same only since the arrival occurs as a Poisson process. So we found the limiting probabilities at the departure epochs, but since the arrival follows a Poisson process, the limiting distribution of number of customers in the system at the arrival epochs and the departure epochs and at the arbitrary time points all are same. This is a standard result which we shall be using without proof. Now we can find out the average measures. Average number of customers in the system in steady state is given by differentiate the probability generating function and substitute z is equal to 1 will be the average number of customers. If you do the simplification, you will get rho times rho plus lambda square expectation of the service time distribution whole square expectation of b square divided by 2 times 1 minus rho, and this equation is known as a PK mean formula. The previous one was the PK formula because that gives the steady state probabilities, whereas this gives the average measures, therefore this is called the PK mean formula. Here expectation of b square is the second order moment about the origin for service time. This result holds true for all scheduling discipline in which the server is busy if the queue is non-empty. The expected system size Ls can be computed without Vz also. because if you know rho as well as if you know the expectation of B square, you can find out the expected system size. Now we are deriving the LS in a different way, not via the pk formula. So the derivation is as follows. So the LS can be written in terms of expectation of xn plus 1, and you can find out expectation of u of xn using this. You will get it's equal to rho, and after you do the simplification, you can get the expectation of xn plus 1 square also in terms of expectation of xn square as well as expectation of an square. So once you know the expectation of xn plus 1 square and the variance of arrival, where variance of arrival means the variance of number of arrivals during a service time, you can get the expected number of customers in the system in steady state. So this is called the pk mean formula without using the pk formula. Once we know the LS, that is average number of customers in the system, you can find out the LQ, that is the average number of customers in the queue, and TS is nothing but the total time spent in the system, and the TQ is nothing but the TS is nothing but the average time spent in the system, and the TQ is the average time spent in the queue. So using Little's formula, you can find the all other measures. As a special case, if the variance is 0, variance of service time is 0, that means it is a MD1 queue, then you can get the average number of customers in steady state will be rho plus rho square divided by 2 times 1 minus rho. Here the rho is nothing but lambda by mu, where 1 by mu is a constant service time. Alternatively, you can find out the steady state probabilities by solving a V is equal to Vp, and you can use the mean sojourn time, that is 1 divided by mu j for the state j. Then you can find out the steady state probabilities. Pj is nothing but average sojourn time multiplied by the steady state probabilities of embedded Markov chain, the way we have done it in the semi-Markov process. As a special case, you can verify when the service time follows exponential distribution with the mean 1 by mu, you can get the one-step transition probability matrix in this form for the embedded Markov chain. Then you can solve V is equal to Vp with the summation of Vi is equal to 1, you will get Vj's. Then if you substitute the Vj's as well as substitute the Vj's, then you can get the steady state probabilities for the M1Q, that is same as 1 minus rho times rho power j. For any MG1Q, you can find out the average time spent in the queue, that is a mean queuing delay. And once you know the mean queuing delay, if you add the average time spent in the, you can get the average time spent in the system by adding average service time, that is 1 by mu. So the TS will be TQ plus 1 by mu, that will be the average time spent in the system. By Little's formula, you can get LS. LS equal to lambda times TS. You know the TS, so from that you can get the lambda S, which is same as what you got it in the pk formula, pk mean formula. As a special case, when the service time is exponential distribution with the mean 1 by mu, you can get the average time spent in the average number of customers in the system will be rho divided by 1 minus rho. This is same as the average number of customers in the MM1 queue. In this derivation, we assume first come first served scheduling to simplify the analysis. But the above formula are valid for any scheduling discipline in which the server is busy if the queue is non-empty. The no customer departs the queue before completing the service, and the order of service is not dependent on the knowledge about the service time. If these conditions are satisfied, then for any scheduling discipline, you can use the above formula of average number of customers in the system. So using Little's formula, you can find out the average time spent in the system. Lambda times T is equal to LS. As a simple example, consider the people entering cricket stadium at New Delhi to watch the cricket match. There is only one ticket line to purchase tickets. Each ticket purchase takes an average of 20 seconds. The average arrival rate is 2 persons per minute. So the question is, find the average length of queue as well as the average waiting time in queue, assuming the queuing model is a MG1 queue. With the service follows a uniform distribution between 15 to 25 seconds. With this given information, you can get the departure rate, arrival rate. Because it is 20 seconds per person, therefore the rate will be 3 persons per minute. And the arrival rate is 2 persons per minute. Therefore, you can get lambda, that is 2 by 3. So it is a irreducible positive recurrent Markov chain. Therefore, the steady state probabilities exist. And given the steady service time distribution is uniform distribution between the interval 15 to 25, you can get the measures of steady state probabilities as well as all the average measures. Now we move into the second non-Markovian queuing model, second non-Markovian system, that is MGCC system, because in this model there is no queuing. The MGCC queuing system, also known as the Erlang loss system, since its development can be traced primarily to the Danish mathematician Erlang. Customers arrive according to the Poisson process with the rate lambda. Service from one of C parallel servers. The service times are assumed to be independent and identically distributed with the finite mean 1 by mu. Because there is no waiting space in the system, arriving customers who finds all C servers busy are lost. Therefore, this system is called a loss system, not a queuing system. For example, lost customers might represent vehicles arriving at a parking garage to find no vacant parking spaces. Our interest is to find out the steady state distribution. The offered load per server, often termed the traffic intensity, is given by lambda divided by C mu. If you denote A is equal to lambda by mu, then the rho is nothing but A by C. Let NT be the number of occupied servers at time t. So NT is a continuous time discrete state stochastic process with the state space S. Define the limiting probabilities. Limit t tends to infinity probability that NT is equal to j, that is pi j, or the steady state distribution. You can find easily, that is nothing but a power j divided by j factorial divided summation I is equal to 0 to c a power I divided by I factorial. So this is a steady state distribution of MGCC loss system. So this distribution is a truncated Poisson distribution with the parameter small a, where a is nothing but lambda by mu. Once we know the limiting distribution, you can find the other measures. The first measure is the Erlang B formula. Because Poisson arrival C is the time averages, that is pasta, we can find the long run proportion of the arriving customers who see C servers busy, that is denoted by Erlang B formula as a function of C and A, where C is the number of servers in the system and A is lambda by mu. That is nothing but the loss probability. That is a power c by c factorial divided by summation I is equal to 0 to c a power I divided by I factorial. When A and C are large, it can be difficult to compute due to the presence of factorials. Due to the presence of factorials and potentially very large powers, a power c. When c is very large, then a power c as well as these factorials giving trouble. So we can use a recursive formula. We can use the recursive formula to compute the Erlang B formula. That is in terms of, that is b k comma a in terms of b of k minus 1 comma k, b of k minus 1 comma a, with the initial condition b of 0 comma a is equal to 1. So that means to find the value of b of 1 comma a, you use b of 0 comma a. Then to find the b of 2 comma a, you use the value of b of 1 comma a and so on. So finally you can get b of c comma a. In this recursive formula, we are avoiding the factorial as well as the large powers. The Erlang B formula is a fundamental result for telephone traffic engineering problems and can be used to select appropriate number of servers need to ensure a small portion of lost customers. So this is a way, using the Erlang formula, we can find out or we can select appropriate number of servers for the MGCC loss system. For a fixed A, where A is lambda by mu, the Erlang B formula or the blocking probability or loss probability monotonically decreases to 0 as a C increases. Whereas for a fixed C, where C is a number of servers, the blocking probability monotonically increases to unity as lambda by mu increases. As a special case, when the service times are IID random variables, each having exponential distribution with the mean 1 by mu, the system becomes MMCC loss system. So you can have a Erlang B formula for the MMCC system also, with the assumption of service times are IID random variables, each having exponential distribution with the mean 1 by mu. Related to the Erlang B formula, we are going to discuss the other one called Erlang C formula. This is for the MMCC system, not for MGC system. This is for the MMC system, which includes a infinite capacity queue to accommodate arriving customers who find all C servers are busy. That means this is a queuing system, queuing and delay system. We have C servers and infinite capacity queue to accommodate arriving customers who find all C servers are busy. So corresponding to MMC queuing and delay system, we have the formula called Erlang C formula or Erlang delay formula. In this model, the PC is interpreted as a long run proportion of customers who experience a delay before their service begins. The model assumes the customers are willing to wait as long as needed to receive service. So the Erlang C formula is nothing but the blocking probability for the MMC queuing and delay system, that is in terms of, that is written in this form, a power c divided by c factorial multiplied by 1 minus rho divided by the summation form. Since it is a queuing and delay system, you need an additional condition to have the Erlang C formula. The additional condition is it requires the traffic intensity rho does not exceed 1. That means as long as rho is less than 1, the system is stable. The corresponding MMC queuing and delay system will be stable. Hence the steady state probabilities exist. And once the steady state probabilities exist, you can find the loss probability. And that loss probability is same as Erlang C formula. So to have a Erlang C formula, it requires the traffic intensity rho has to be less than 1. And note that the above result does not hold for arbitrary service time distribution. So this Erlang C formula is valid only for service times are exponentially distributed, not for arbitrary service time distribution. Whereas Erlang B formula is valid both for MGCC loss system and MMCC loss system. Erlang C formula is valid only for MMC queuing and delay system with the restriction rho has to be less than 1, whereas Erlang B formula, the value of A is lambda by mu need not be less than 1 because that is a finite capacity and loss system. In this, we have discussed the non-Markovian queues, in particular MG1 queuing system, MGCC loss system, MMCC loss system, Erlang B formula for MGCC loss system as well as MMCC loss system, and finally we have discussed Erlang C formula for the MMC queuing and delay system. With this lecture 4 is completed, and here is the reference for lecture 4.